Hello, Science 30s. In this video, we're going to be looking at how you pay for electricity. So how is that cost determined, and mostly from a mathematical point of view, and instead of the political and economic point of views, but from the mathematical point of view, using our formulas today. So what we're going to be looking at today is going to be this formula right here. Energy in joules is going to equal power in watts multiplied by time. And time in this case is seconds, or actually usually hours. I know it says seconds here, but usually we use the kilowatt hour. So again, here you see that P is in watts, whereas we're actually going to be using kilowatts, and time is in seconds, but we're actually going to be using hours. So that's a really important difference to notice when you're doing your work compared to the formula they listed there. So here's our first example. So this will take us a little bit to get through, and then I just have another little example, and then we're done for this video. So what you may not know is that when you turn your power off on your devices, there often is a bunch of standby power that is still going through that device. So for example, if there's an LED display, that needs power to run. In fact, there's been some studies that have shown that over the lifetime of a microwave, the microwave will use more power by powering the clock on it than it will by heating your food. Now, of course, that's over the lifetime. You think about that, the clock is on 24/7, whereas how often are you using your microwave? And so, yeah, there's a lot of there. I mean, again, there's some heavy users of microwaves where they're definitely using more power by using their microwave for heating food. But there's going to be some people who barely use their microwave who are going to use more power to power that clock. And so once again, what we're going to do in this example is we're going to take a look at how much power that is actually using. We often lose sight of that, guys, when we think about populations. How many, in this case, it's an old example, but I think the example will still stand true. We're looking at TVs and VCRs. Now we're looking at DVDs, players, Blu-ray players, PS3s, and PS4s, the Xboxes, okay, all these things that when you turn them off, do they still consume power? And a lot of them do. Now, we do have a program in Canada called Energy Star, and the Energy Star program does, if you buy an Energy Star product, you're usually buying a better product as far as power consumption. But anyways, let's get into the example here. So most models of TVs and VCRs use electrical energy even when they are turned off. This standby power is used to run clocks in VCRs and to provide an instant on feature, allowing home electronics to become operational with a click of the remote control. Average values for standby power are about 3 watts for a VCR and 5 watts for a TV. Since this power is required 24 hours a day, the electrical energy consumption is significant. So determine the electrical energy required to supply 8 watts of standby power for both a TV and VCR during 1 year. So 1 year there. Explain or express your answers in kilowatt hours. Okay, so for A, there's a lot of steps we have to go through for this one. First of all, we have the power, which is equal to 8.0 watts. Well, that's no good for us. We can't be in watts. We need to be in kilowatts, because you see here, express your answer in kilowatt hours. So we know that there's 1,000 watts in a kilowatt. So if we take it like this, we put our kilowatts on the top, put our watts on the bottom. 1,000 goes down here then, 1 goes up here, our watts cancel out, and we're left with 0.008 kilowatts, or 8 times 10 to the negative 3. So there we are. That would be, and of course, if we want to do sig digs, that would actually have to be 80 there. So the next thing we have is the time. the time, we're going to assume this is not a leap year. We're going to assume 365 days in a year. But of course, we need to be in hours. So how many hours is in 365 days? Well, there's 24 hours in a day. So 24 hours in one day. The days cancel out, and we are left with 8.76 times 10 to the 3 hours. Okay, so now we have our P, we have our T. Now if we go back to our formula right here, okay, E is equal to P times T. And so that's what we need. We now need to figure out the energy. So the energy is going to be E is equal to P times T, which is going to equal 8.0 times 10 to the negative 3 kilowatts. And we're going to be multiplying that by 8.76 times 10 to the 3 hours. And we get our total energy for the year is going to be rounded off, is going to be 70 kilowatt hours. Okay, so 70 kilowatt hours. Now what does that mean? Well, what we're going to do now is we're going to take a look at what that means. So that means that now in this example, once again, there's in B here, they're saying if the price of electricity is 9.3 cents per kilowatt hour. That's fairly, we're a little bit lower than that right now. I think it's about 6 or so right now. But today, or right now, it's May. And May is a relatively low month usually. Power is usually going to, or electricity will usually increase in price in the July, August months when a lot of people are using air conditioners, and in the January, February months when a lot of people are using heaters. So when you a lot more of those things are happening during those times, a lot more electricity usage. And so you see the cost of electricity go up. We'll stick with this example, and we'll stick with the 9.3 cents per kilowatt hour. Okay, so that means B. So what we need to do, so first of all, we're going to say that the energy is going to equal 70.08 kilowatt hours. Okay. And then I'm going to have to move away from the question here. We'll just remember the 9.3 cents as I write it down right now. And we're going to say that the cost equals 9.3 cents per kilowatt hour. And so our cost then is going to equal, I'm just going to do this. There's no formula on your formula sheet for this. This is obviously just, we have kilowatt hours here in the numerator, kilowatt hours here in the denominator. So we just need to multiply these two. So we're just going to go 70.08 kilowatt hours. I kept the unrounded answer from A. And then we're going to multiply that by 0.093. Sorry, that's in dollars per kilowatt hour. Kilowatt hours will cancel out, and we're left with $6.52. So that's how much it would cost yearly for one person to run one TV and one VCR, even if they never ever turn them on the entire year, but they were plugged in. That's how much it would cost them. Doesn't sound like much, but take a look at this. Now we get into the staggering effects of what happens when we take a look at a whole population. So there are about 2 million TV VCRs that operate. Now, again, this is just in Alberta. Okay, this is just in Alberta. Use this fact to estimate the total annual cost of maintaining standby power for all of these devices in Alberta. So 2 million. So if we have 2 million devices, I keep forgetting to switch my pen there. So if we have 2 million devices, okay, obviously we would just convert that. We can just write that as 2 million, obviously, as well. And then we're going to multiply that by $6.52. Then we get $13 million. So this is costing Canadians or Albertans $13 million. And keep in mind, this is just for TVs and VCRs. And now again, these numbers might be better now a little bit, but I would probably hesitate to say no because we have more devices now. We have way more devices. We have, how many TVs do you have in your house? How many DVD players do you have in your house? How many gaming systems do you have in your house that are all using standby power? And then that got me into thinking about Canadian numbers, and I actually found this stat on the Manitoba Hydro Canadian standby power. I found this number on Manitoba Hydro, and what it says is that Canadian standby power consumption is 5,400,000,000 kilowatt hours. So this is Canadian standby power consumption. So now let's stick with that same 9 cents. What if it was 9 cents per kilowatt hour? So this would obviously be switch to my pen again here, 5.4 times 10 to the 9 kilowatt hours. And what if we multiplied that by $0.093? Okay, that would be 9.3 cents. And that should obviously be per kilowatt hour. That cancels out, and we are left with, I actually didn't do this problem, so let me figure this out for you. That would be 5.0 times, well, I'll just write the whole number out because it'll be easier for us to see it that way. 50220000. So this would be $500 million is how much we're spending on standby power in Canada in a year. I have no idea if that's counting just residential, if that's counting if you think about all the computers, guys, in all of the office buildings downtown. Very few people shut those computers off at night. They leave them in standby mode, which uses power. Monitors are not being shut off; those use power, and so again, we talk about all these standby power devices, guys, which makes you think you should probably be thinking in your houses how you can reduce that. Okay, so that's how you pay for electricity. You'll have a couple. You'll have to be able to explain that in your portfolio. Thank you very much.